Hello everyone and welcome to another video. Today I would like to talk a little bit about performance of a second order system. Or sometimes this is also known as time domain analysis. Or you might also hear some words and keywords called performance metrics. Okay, so the concept here today is, like the title suggests, we're interested in looking at a second order system. So our second order system might look something like a y double dot of t plus 2 zeta omega n y dot of t plus omega n squared y of t is equal to omega n squared r of t here. So here's my second order linear non-homogeneous differential equation here, right? And I think maybe the easier way to think about looking at this is, instead of looking at this right now as a differential equation, how about considering this as a transfer function? So if we go ahead and make an assumption of no initial conditions, right, we could go ahead and take the Laplace transform of both sides and try to solve for the ratio of the output over the input in the Laplace domain, right? And if you were to go ahead and do that for this system here with no initial conditions, I think you could quickly see that this is going to turn into something like an omega n squared over s squared plus 2 zeta omega n s plus omega n squared. So this was our standard second order transfer function written in standard form with the zeta and omega n's here. So in this case, why don't we go ahead and call this entire transfer function g of s, right? And now we can visualize this as, again, it's a dynamic system where you have inputs of r, and coming out of this is an output of y. And maybe we should quickly mention here in this situation, zeta is referred to as your damping ratio. And in today's discussion, let's consider these to be greater than 0. And omega n is referred to as the natural frequency of the system. Again, this should be positive for stable systems here, okay? So what I'd like to do here is now consider, I think you probably have some feel for this here, but what the idea with performance of this system is, it's really asking, if you give this system some type of input over here, what type of output might you expect here? So if you knew something about the natural frequency and the damping ratio of this system, would you be able to predict, if you say gave this thing a step input of magnitude A, what might the output on this side look like, right? It might look something like that. Could we predict characteristics of the output based on just the physical parameters of the system, like zeta and omega n? Like, for example, how much overshoot would there be? How long would it take to settle? Things like that are what we would like to answer today. So in order to do that, I think what we should do here is we are going to develop some of these performance metrics in response to a step input. So in other words, the particular input that we want to look at today is a step of magnitude A. So in other words, it's just like the picture we saw over there, that the input is just sitting there at 0, and then at time equals 0, we hit it with A units of force or whatever the input is to this system. So I think you all remember now that in the Laplace domain, right, a step of magnitude A looks like A over S, right? This is the Laplace representation of this step function here. Okay, well then what we can do, if that's the case, we can easily get the output of this system, right, what this is going to do in the Laplace domain. So we could go ahead and compute the output from the transfer function, right? So the output here, it's just going to be the transfer function multiplied by whatever input here, right? So our transfer function is pretty simple, right? It's omega n squared all over s squared plus 2 zeta omega n s plus omega n squared, right? This times A over S here, right? And this basically is going to give you what the system does in the Laplace domain here, right? But in order to come back here and do performance or time domain analysis on this, I would like to understand, what does the signal look like in the time domain here? So I need to get this thing into the time domain, so we just need to inverse Laplace transform this whole thing, right? So I'll just write down that we need to do an inverse Laplace transform to get y of t, right? I want the signal in the time domain. So to do that, right, you could go y of t, it's just the inverse Laplace transform of y of s, right? So you need to do partial fraction expansion or whatever you like to do in order to take the this expression in the s domain or the Laplace domain and get it back into the time domain here. I am not going to be able to do that on the board in any reasonable amount of time here, so let's go over to Mathematica and see what it gives us for this, okay? So let's head over there and just plug this into Mathematica here. We'll have Mathematica do the inverse Laplace transform of this signal here. All right, so here we are with Mathematica. So maybe the first thing we should do is let's define our transfer function g of s, right? We said that was omega n squared all over s squared plus 2 zeta omega n s plus omega n squared. That was our transfer function. And now let's go ahead and compute, well, maybe we should put some comments in here. Define transfer function. And now let's go ahead and compute r of s, right? This is the response to a step of magnitude a, right? So we said r of s, right, is just going to be g of s times the input, which was a over s, right? Okay, that's perfect. And then lastly, what we need to do here is perform the inverse Laplace transform to go back to time domain, right? Okay, so we just need to go inverse Laplace. Why is, come on, why, I'm not getting the tab complete. Okay. Inverse Laplace transform r of s going from the s to the time domain, right? So there we go. Let's shift enter this and see what we end up with. So, yuck, that's kind of ugly here. I wonder if we can do anything about this. Maybe let's simplify this. Whoops, I spelled simplify wrong. That's a little better here. I think we can make also, we can tell simplify that, hey, you know what? Omega n is going to be positive and zeta is going to be positive. Let's see if that helps our situation. Yeah, that helped it a little bit here. And you know what? Maybe let's break this all up into a whole bunch of terms. So maybe I'll just simplify it and then expand it, which is a little bit silly here because I guess you're undoing the simplify by expanding it here. But you see, we end up with a bunch of terms here. In the interest of not breaking our stride too much, what I would like to now show here and maybe prove to you is, after you do a lot of manipulations here, if you want to do some by hand manipulations, you can simplify this to a nicer form. So maybe let's just write that down here as text here. Let me just say you can simplify / reduce this to the form of, and to avoid myself plugging this all in incorrectly, I've just got it all prepped here, but you could basically make it look like this. If you look at it long enough, it's you can see there's a bunch of e to these something terms here, and there's a bunch of coefficients here, but you can basically get it to look like this here, where here's your coefficients, little a, little b, and here's what sigma and omega are, okay? And you obviously don't want to take my word for this here, right? We want to make sure that that actually is true. So maybe let's come back up here, and we'll call this y step of t, right? Because this is the actual output in response to a step of magnitude a, okay? And now we claim it can look like this. So you know what? Let's make another thing, maybe y step check, right? And we said that, all right, this is supposed to be a plus e to the minus sigma t times the quantity a e to the minus omega t, right? Minus b e to the positive omega t. And parentheses. Great. That's what we claim here. And now what we want to do here is let's make our substitutions of A, B, sigma, and W and check to make sure that they are the same here. So let's go ahead and verify that y step is the same as y step check. right? That those two are the exact same thing. So what we need to do here is probably do something like, all right, I need to double check is y step equal to y step check of t, but then I need to basically make all of those replacements here. We said that, oh boy, to plug all those in. Again, I think I'm going to screw that up if I go ahead and try to fat finger plug all that in. So I've got all of that input sort of prepared already. So let's just do it like this. So does everyone agree here? All I'm doing here is the left-hand side is this giant expression here with all the appropriate substitutions put in. And now we're just going to make sure that that still equals y step here. So if I shift enter that guy, yuck, didn't seem to help too much. Let's maybe ask it Mathematica to simplify. And yay, there we are. It is true here. So this actually is a perfectly valid alternative representation here. So let's head over to the whiteboard with this representation and see if there's something else we can do to make this a little bit more intuitive. All right, so we showed that the step response in the time domain was given by this. This was an alternative format to write this here. Let's go ahead and make a note that, you know what, let's go and substitute in our expression for omega here. We're going to play a little bit of a small trick here. So again, let's write this as a e to the minus sigma t times little a e to the, let me see, omega was square root zeta squared minus 1 here times t, right? Minus b times e to the square root zeta squared minus 1 t here, something like that. Okay, now what I'd like to do here is, you know, I could put a minus 1 in front of this and kind of flip the order here, right? Well, maybe let's make a note here. So let's just examine that term right here, right? This is zeta squared minus 1 here, right? I could go ahead and write this as negative 1 times 1 minus zeta squared. Everyone agrees that's the exact same thing here. And now I could also write this thing as square root of minus 1 times square root of 1 minus zeta squared, right? This is just I, right, the imaginary number. So I could write this like such. Would everyone agree that's the same thing here? So let's go ahead and do that and put that in up here. So I could rewrite this thing as a plus e to the minus sigma t times little a e to the, I want to make sure I get this right here. So e to the, wait a second, where did I drop a negative? Sorry, I dropped a negative sign. Sorry, there should have been a negative sign right here, right? Negative, right. So this should be negative I square root of 1 minus zeta squared omega, wait a second. Did I drop another, crud, I got, wait, yeah, sorry. Boy, that was really sloppy. There should be an omega n here and an omega n. Yeah, there we go. Okay, so there we go. Now we're on the same page. Okay, omega n t, right? Minus b e to the I square root 1 minus zeta squared omega n t, right? Okay, and then also, I guess if you notice here with a and b, there's that same term down here in the a and b. So again, we could flip the order of this and introduce an imaginary number in here if we wanted to here. So for example, maybe I'll just do it for b since I'm not going to have enough room here for the a term here. But this could be 1/2 a plus a zeta all over 2i square root of 1 minus zeta squared, right? We're going to do this exact same little trick here. All I want to do is I'm basically just introducing a bunch of imaginary numbers here. Now, if you look at this here, for example, each one of these exponent terms, right? This sort of looks something like e to the ix or something like that, right? Here's the I, and then you got some other kind of junk up there, right? What I'd like to do now is basically use our trig identity here, or our exponent, basically turn this exponent into a trig series here, right? So if you remember e to the ix, this is the same thing as cosine x plus I sine x. Right? So I would like to rewrite all of these exponents as cosines and sines here, right? So if you do that, and actually if you take into account all of these i's, what's kind of interesting about this here is if you do a bunch of boring manipulations here, right? So algebraic manipulations. Well, I guess you make this substitution, right? You make this exponent to trig substitution. You make a bunch of boring substitutions here. You can write this thing, the whole y term can be rewritten with sine and cosines to look like this. It looks like a minus a e to the minus zeta omega n t times the quantity cosine of square root 1 minus zeta squared omega n t plus zeta all over square root 1 minus zeta squared sine of square root of 1 minus zeta squared omega n t. Right? Which is, again, kind of interesting because now there's no imaginary numbers, I guess, obviously assuming here that zeta is in the range of 0 to 1, right? Otherwise, you could pop out imaginary numbers here and this might change. But if we're in this regime, this is what we end up with. And you know what? Why don't we go ahead and redefine, let's redefine this quantity right here, this minus, or the sigma omega n here. Let's call this thing just, how about sigma here? And then here in the cosine and sines, this is also a kind of an interesting observation here. We see that this thing oscillates at the angular frequency here of this times this. Let's call this omega d here, right? And again, here you see this term omega d, or your damped natural frequency is what this is sometimes referred to as, right? A misleading name of this omega n is called the natural frequency, right? And people always assume that, well, if that's the natural frequency of the system, that must be the frequency at which it oscillates. No, it actually doesn't here, right? In response to a step, when you hit this thing with a step of magnitude a, the angular frequency of these cosine and sine waves is actually omega d, which is really close to omega n unless you have a non-trivial amount of damping here, right? So anyway, with those simplifications, we can write this whole thing to look like y of t is equal to, let's get our last final form that we're going to use and start messing with here. This is a minus a e to the minus sigma t times cosine omega d t plus zeta all over square root 1 minus zeta squared times sine of omega dt. Here and here, sigma is going to be the product of zeta and omega n, and omega d is square root of 1 minus zeta squared times omega n. And again, this is sometimes referred to as your damped natural frequency. Great, so I think we box this up because this is how the system is going to respond to a step of magnitude a here, right? And again, I think we made a bunch of claims like all of these dot, dot, dots and things like that. So we better go back and let's double check that this solution actually does solve the original differential equation we started with, and it has appropriate initial conditions of 0 position and 0 velocity here. So I don't want to do that on the board, so let's jump back to Mathematica to double check this solution for reasonableness. All right, so let's go ahead and define the cosine slash sine representation of y of t here, right? And I think we said that's, let's call it y step, how about trig or something like that. Okay, so I think we said that was a minus a e to the minus sigma t, whoops, I missed the bracket, a e to the minus sigma t, right? This whole thing now is times the quantity cosine omega d t plus zeta all over square root of 1 minus zeta squared times sine, whoops, sine of omega dt here, right? That was our expression here, and we said that sigma was given by the product of zeta times omega, whoops, omega n, and omega d was going to be what? It was square root of 1 minus zeta squared times omega n, right? Okay, so here is our here's our candidate solution, right? So we better go ahead and now verify that this satisfies the original second order ODE, right? So just to refresh your memory, I think we said that that was y, whoops, I'm just going to rewrite it real quick. Y double dot of t plus 2 zeta omega n y dot, come on, let me get the subscript right, y dot of t plus omega n squared y of t. Oops, sorry, that should be a lowercase t, or this, right? This should equal, what do we say, omega n squared r of t here. Or in our case, r of t was just a, right? Because it was just a step. So in the time domain, this is what we need to check, right? So let's build up the left-hand side and check that it equals the right-hand side. So what we need to do here is let's go ahead and take the second derivative of this thing. So dy step trig, right, of t with respect to t twice. Okay, so that's y double dot plus 2 times zeta omega n y dot, right? That's y dot plus omega n squared y, right? This whole thing better equal omega n squared times a. And when you shift enter that, we get a whole bunch of gobbledygook here, but let's ask Mathematica to simplify, and yay, look at that, it's true. So yes, this actually does satisfy the differential equation here. Let's verify that this has 0 initial conditions, right? Because if you remember, that was an assumption we made when we developed our transfer function here, right? So in 0 initial conditions means I better make sure that here, y at time 0, that should equal 0. And it does. And what we should also check here is its first derivative at time 0 is also 0. So I need to do the first derivative. So here is y dot. And I want to now look at this when t is equal to 0, right? So, hey, look at that. Both of those two things are 0. So I think we are good to go here. This representation should basically be able to solve the differential equation and basically satisfy our equation. So maybe since we're sitting here in Mathematica here, let's try to get a visual of what this thing looks like. So let's go ahead and just say visualize the function y of t. Okay, so I could go ahead and let's pick some, we got to pick some values of things like the omega n and the zeta, the amplitude here. So let's say choose specific values to use for plotting, right? So I need to pick amplitude that I'm going to hit this thing with. So maybe let's say a given is like, I don't know, 2.3 units or something like that. And then the natural frequency of the particular system I want is, I don't know, how about 1.5? And how about the zeta, that I'm interested in here is something like 0.2 or something like that. Okay, so if those are our specific values, what I can now do next is let's go ahead and, how about plot the function, right? So all I need to do here is just say plot y step trig of t, right? And then let's make all those replacements here, right? So a is now going to be a that I'm interested in visualizing here. Zeta is going to be zeta given, and omega n is going to be omega n given. And let's plot this thing from t equals 0 to, I don't know, some t final. And maybe we should define that up here. T final, I don't know, 15 seconds or something like that. Okay, great. So if we do this and shift enter this, here we are. This is what it looks like, and actually it looks like it cut off some of the plot. So tell you what, let's do our good old plot range all. There we go, so we can see the entire function. And yep, it looks like it starts at 0, has 0 slope, but pretty rapidly it comes up here, and you know what? Let's plot two things at the same time. So let's also plot the step input here. So the first one is, whoops, let me put a little comment in here. So this first thing we plot is show y of t, right? The response, right? And now let's also show r of t, or the input here. So let's go ahead and plot, well, I guess it's just a, right? And I guess we got to make that replacement here of a goes to a given. Well, that was kind of a verbose thing to say, but I think you get the point here. Okay, let's plot it like this here, and let's change its, let's make it red just so it stands out from the other one. Okay, so we shift enter that. Here we go. So look, this is pretty darn perfect here. So apparently what this system does here is it starts from 0. It starts trying to go to wherever you put as input here. Eventually it settles out so that the output is equal to the input. But on the way to getting there here, right, you notice here it way overshot. And then it took a little while to come back and settle here. So this sort of sets the stage for the next portion of our talk here is, what if we want to be able to quantify or measure
how far did it overshoot? How high is it? How long did it take to get to this first peak? How long does it take to settle? All of these different topics here. We would like to come up with some analytical expressions here so we understand how the natural frequency and the damping ratio are going to affect the overshoot or the settling time, or basically how it's going to affect the response of the system. So why don't we draw this picture back up on the board and examine some critical portions of it.
All right, so I've redrawn that graphic or that example plot here on the board here. So the red is the amplitude or the track value that we're trying to go for here, right? Is a step function of magnitude A here, and the blue is the response y of t here, right? And I've also left our expression up here which describes this blue line, because we're going to see that for the next couple minutes here, what we're going to be doing here is examining this equation here and trying to make some simplifications in various scenarios. So some of the things you might want to know about this blue curve here is, first of all, one of them might be the time to first peak. This is sometimes referred to as TP. So what does that look like? So what I'm basically asking for is, how long does it take to go from 0 up to this first peak here? So right here. So what I'm looking for is down here is I want this time, here's TP, right? Okay, so if you think about this long enough, it's actually not that hard to get to. What we should do here is I should really solve for where the derivative of this function is 0 here, right? Because where the derivative of this guy is 0 is basically where it's either at a maximum or a minimum or a maximum or a minimum. It's one of these peaks here, right? So let's go ahead and just take the derivative of this thing and basically solve for t. So if I go ahead and take the derivative of that thing, I think you're just going to have to take my word for it, because I don't want to do it all by hand here, but basically y dot of t, right? This could be rewritten here as a times omega n all over square root of 1 minus zeta squared e to the minus sigma omega n t times sine of square root 1 minus zeta squared omega n t. Okay, that is what we end up with here. Now I'm just slightly... Yeah, because these two cosine sine waves, because they're at the exact same frequency, right? A cosine wave and a sine wave at the same frequency can be rewritten as a single sine wave. So if you do that and then take the derivative, this is what you get. If you went over to Mathematica and you basically, if you remember, we had our function y step trig, right? If you just went ahead and took the derivative of this thing with respect to t, right? This is what you would end up with here. So this is what we get here. So now all I need to do here is basically solve for when the derivative is equal to 0, right? So I set this thing equal to 0 and now solve for t, right? And again, I think if you do that and simplify this down here, what we could end up with here is, let's work through this a little bit here. We notice, well, actually, this is not that bad. This entire thing right here, this is never equal to 0, right? Because this is an exponent here, so it'll never actually truly go to 0. None of these are 0 here, right? So I can just get rid of that on the other side. So this whole thing, this is gone. We end up now with sine of square root of 1 minus zeta squared omega nt is got to equal 0, right? And if you look at this long enough, we see that, okay, this evaluates to 0 whenever the input or the argument to sine is some integer multiple of pi here. So in other words, I need square root of 1 minus zeta squared times omega nt to be equal to some integer value of pi, like k pi, right? So k has to be 1, 2, 3, etc., but some integer value. So great, solving for time, we basically get our time peak, right? So the time to the peak here, or to, well, maybe we should write it like this. The time to any particular peak, let's call it maybe lowercase tp, right? Is just k pi all over square root of 1 minus zeta squared omega n, right? Okay. Now, if I want the first peak here, what's interesting about this is I actually have to use the k equals 1, not k equals 0. K equals 0 actually corresponds to over here, right? Because if you think about it long enough, we showed earlier the initial conditions, the derivative of the function right here at time equals 0 is actually 0 here, right? So if you plug in k equals 0, you get TP of 0, which corresponds to this point right here. Okay, so I actually want the first point here. So the time to first peak, which we were calling capital TP, is actually what? It's just k equals 1. So we end up with pi all over square root of 1 minus zeta squared omega n. Right? Great. So let's box this up here. So this is actually pretty darn cool here, because what it's telling us now is that the second you know the damping ratio and the natural frequency of your system, you don't have to run any simulations or solve any trig or do anything like that. You can tell exactly how long is it going to take before it reaches that first peak here in the function. Okay? Great. So you know what? If we have the time to first peak, it actually would be really, really easy now to get the amplitude at the first peak. Whoops. Amplitude at first peak. And this is sometimes referred to as MPT here. Okay, so graphically over here on the picture, right, where that looks like is that's over here. So here is, we better move this thing here. Here is MPT, right? That's the magnitude at the first peak. And as you can probably imagine, this is actually really easy. If I already have the time at the first peak, all I have to do is evaluate the function, right? Evaluate this function here at the peak time. So I just need to go here, y, and look at this at capital TP, right? So in other words, take that entire big thing of junk here, and everywhere you see a t, you replace it with this expression down here. So to use some Mathematica terms here, right? So you would slash dot, and everywhere you see a t, replace it with this thing down here, right? Pi over square root of 1 minus zeta squared omega n. Right? That's all you do. I don't think we want to do this on the board, so let's just write it down here. So this is going to give you the magnitude at the first peak, or MPT, and what that ends up being here is A times 1 plus e to the negative pi zeta all over square root of 1 minus zeta squared here. Okay, so here we go. Box this up. So the magnitude obviously depends on how hard you decide to hit your function, or how much of the input amplitude it is, right? That's how high the actual peak is. Maybe what's interesting is we should have actually maybe noticed this down here when we looked at the time to first peak here. Notice here the time to the first peak is not a function of A. So in other words, it doesn't matter if you hit this thing with 1 Newton of force, it will take the same amount of time to reach the first peak as if you hit it with 1,000,000 newtons of force here, or whatever the input is here. In this case, what's interesting about the magnitude of that rise here is, if you look at this, omega n doesn't show up. So this guy is not a function of natural frequency. So the natural frequency has absolutely nothing to do with how high up do you get here on this peak, right? Okay. All right, so we got the time of the first peak, we got the amplitude of the first peak. The next thing you might want to think about here is it's called percent overshoot here, right? You look at this and you see that we went way past the actual desired steady state A value here before we came down and settled. So we should be able to have an idea of how much did we go past here, right? Obviously the amplitude of the first peak gives us some hint of that, but let's formalize this into this concept of percent overshoot. So the next thing we want here, let's erase this side of the board, is percent overshoot, or PO, okay? So the way we can formally define this here, so the percent overshoot is going to be defined here as, you can see here that the amount you went past the desired location, or the steady state value, this thing here, that is, you can actually just look at that, right? That's MPT, right? That's how high you went minus the steady state value, right, of the signal here, over the steady state value, right? And then this gives you a fraction here, so I want to multiply this by 100. So this is the formula here to get us what we're looking for. So again, the way to think about this here is, right, yeah, this delta, well, this is a little bit misleading. I don't want to say it's delta to the A value. I'm trying to actually get it to Y steady state, right? Y steady state just happens to be, in this case, is the same thing as A, but you don't want to use A in this equation. You always want to use Y steady state here, right? So the distance between the steady state A value and this peak here, right? Here is MPT minus Y steady state, right? And then this distance here is Y steady state. So you can kind of see that the ratio of this to this gives you an idea or an estimate of how far over did you end up going, right? Okay, so if this is the case here, what do we have to do? So in this particular situation, we make a note here that Y steady state is equal to the amplitude A, right? So again, let me belabor the point here, right? This is for our particular case, although this analysis that we're doing is going to work for any particular thing where you might not have a steady state of the actual amplitude of your function. We're just using that scenario here because it makes the math a little bit easier. Okay, so let's plug all of this in here. So again, so now my percent overshoot, it's just going to be MPT minus A all over A times 100, right? So we already had an expression for MPT, which unfortunately we just erased here. So you plug that in, you do all this math here, and you simplify, and you end up with this kind of interesting expression. So percent overshoot is going to be 100 times e to the minus pi zeta all over square root of 1 minus zeta squared. Great. So again, if you look at this thing, you notice here that the interesting observation is it's not a function of omega n. So, in fact, and it's not a function of A either. So here, this is actually fascinating here. The percent overshoot, or how much you go past the steady state value of your signal, has nothing to do with the natural frequency and has nothing to do with the amplitude. It only matters the damping ratio of your system. So the second you know the damping ratio of this system, you know how far you're going to overshoot here. Nothing else matters here, at least for this linear second order system that we're examining here, right? Okay, great. All right, another thing that we might want to know now is, okay, we understand how far you overshoot, but how long is it going to take me before the signal reaches some bound here of the steady state value here, or how long does it take to settle down? So here's our next discussion here is of settling time. So let's look at settling time. Okay, so settling time here, or referred to as TS, right? We can go ahead and easily define that, I think, using just an English word definition here. So the settling time here is basically the time elapsed before the signal returns and remains, this part is key here in the definition, and remains within a specified percentage of its final value, right? Okay, so the picture that goes along with this here is now the final value here is this blue line here at infinity here, right? Not the red line here, right? It's the blue line here, right? Now what I want to do here is I want to pick some little band above and below here, which is some percentage of this steady state value. So, you know, some percentage of Y steady state. Maybe I want, you know, 10% or 20% or 50%, but I'm going to define a little band here. Whoops. Like this. Right? And now what I want to do here is I want to calculate or find out when does the signal return and remain in this bound. So obviously you can see why that and remain part is critical here, because over here, this is the first time the signal returns to within this band, but it sure doesn't stay there, right? It blasts out the other side of the band. Similarly down here, so in this picture, here is my settling time, right? It's going to be this, let me think, yeah, right here. This point right here, let me make sure I draw this accurately, right here. This is the first time the signal actually stayed and remained within my band here. So I'm looking for that settling time value here, okay? All right, so the way we're going to get this here is, again, remember here that here's our expression for the for the blue line here, right? Let's calculate the deviation the system has from its steady state value at any given time here, right? So let's go ahead and define a deviation function, right? It's pretty simple to define here. Let's go ahead and say that the deviation function is called g of t, and this is just how much is the signal away from its steady state value, right? That's pretty easy. Okay, so for our case, let's just plug this in here. So for us here, y of t is that ugly thing over here, right? It's a minus a e to the minus sigma t times cosine omega dt plus zeta all over square root of 1 minus zeta squared sine omega dt, right? Minus y steady state, which in our case was a here, right? So this cancels with this here, right? And this deviation function, if you just look at it now, right, we can plot this deviation function. Here's g of t, right? And if you look at this long enough, this deviation function, it's basically inside here, this is, let's just take a look at this. This is basically a single sine wave, right, at some frequency here, right? So this in here in front, you could think of it almost as like the amplitude of this sine wave. This is sometimes referred to as like your exponential decay envelope, because this is basically telling you an envelope that this sine wave bounces in between here, right? So maybe to look at that a little bit easier here is let me plot this out. I guess we'll use blue like we were doing earlier. Okay, right? So this deviation function is going to look something like this, right? And now this envelope right here, if I plot just this thing right here, maybe we should define this here. Let's define an envelope d of t here. Is just going to be plus or minus a e to the minus sigma t, right? It's just this coefficient right here. What that's going to give you is this envelope, right? That I guess I'm not drawing this exactly the way it should be, but crud, this bottom one looks horrible. It's not touching the, it should touch this thing, right? At the, there, that's a little bit better here, right? So the black here is d of t. The blue here is our deviation function g of t here, right? And now what we can be thinking about doing now is taking this same little band here and drawing it here. Oops, wow, that green is totally not working. Let's try this. All right. Right? So with this band here, what I'm looking for now is, the easier way to do this here is, why don't I just look for when this black line crosses the dashed green line, right? And we notice here that it's actually, it might not be the actual settling time, but it should be a conservative estimate of the settling time here, right? So this point right here, maybe let's call this t settling, and maybe put a little tilde on top of it here, because if let me see if this picture, it kind of draws this, yeah, kind of here. So if that is the settling time, what's the actual real settling time here? Yeah, it would actually be, wait a second. My picture is not very accurate. Yeah, I think you understand what I'm saying here. So basically, yeah, because the settling time, if we were to draw this decay envelope over here, it would be something like something like this, right? And then here's where this TS tilde is going to be, which is going to be a conservative estimate of the actual settling time, right? The real settling time should always be less than what we're computing right now, because there's a chance that the signal is going to stay and remain within the bound here before the exponential decay envelope does. But this is pretty good for government work here, right? So let's go ahead and find this. So in order to find this point, all I need to do is look for when this exponential decay envelope reaches within some percentage of the steady state value. So in other words, let me come over here to get a little bit more room, right? We're looking for here, whoops, I got the wrong color. I'm doing all my math in black. Grab the black pen here. Right, so here's our decay envelope. I'm looking for the settling time tilde here. This thing has the properties that this thing is, I'm looking for when it equals some delta here of y steady state here, right? And I guess, did we actually define what delta was earlier? Here, delta here is some number between 0 and 1 here, which basically represents the fraction here of how much you're going to be looking for. So a delta here of something like 0.05 is like a 5% settling criteria. So you're looking for when does a signal get within 5% of the steady state value here, right? So that's what this delta is. So here's what I'm basically trying to solve here, right? I need to just go ahead and figure this out. So that's not so bad. Okay, so what's this side? This is a e to the minus sigma. Sigma was omega n zeta, right? Times t settling tilde, right? Is equal to delta. What was our y steady state in this case? It was a, right? Great, so this cancels, this cancels. I need to solve for TS, so I think I need to take a natural log of both sides here. And if you do this, I think we end up with, you could solve this for t settling. So you would end up with t settling tilde is basically going to be minus natural log here of delta all over zeta omega n. And here, again, like we said, delta is between 0 and 1. Right? Perfect. Here we go. Here's our expression for settling time here. And again, the thing to notice here, it's not a function of a. So it doesn't matter how hard you hit this system, it's going to take the same amount of time to settle in either situation. Right? Okay, so how about let's go do one last one here. The last one I want to look at here is what's called rise time. Okay, so let's look at the rise time, or TR. Okay, so the rise time, this is defined as the time elapsed between signal reaching a specified start percentage and signal reaching a specified end percentage. So coming back to our figure over here, what it might look like here is typically something like people would use like a 10 to 90% rise time. So in this case, we would look for when does it make 10% of the final of the steady state value. So maybe that's like right here, right? This looks like it's about 10% of where the blue line ends up, and then 90% of it would be, I don't know, something like here or something like that, right? So here, when it reaches the start point, you basically start the stopwatch, and now when it reaches the end point here, you stop the stopwatch. So this delta here is defined as the rise time, right? Okay, so let's go ahead and see if we can get a little bit of insight into this. Let's go ahead and let's assume a 0% start. So now I'm really interested in, as soon as you hit time 0, I want to know how long does it take to get within some delta of the final value. Okay, sorry, I'm back. The camera battery died, so I had to switch it here. So let's come back to where we were. So we're looking for when does the signal at the given rise time that I'm interested in reach some delta here of the steady state value, right? Okay. So in this case, well, left-hand side, it's just this giant thing. Plug in, wherever you see t, just plug in rise time here. And in our case, I think y steady state was just a here. So if you notice here, the left side here, this a is actually going to cancel with these two a's here. So we could maybe get this thing to look like 1 minus e to the minus sigma t times cosine of omega d tr plus zeta all over square root of 1 minus zeta squared sine of omega d tr. This thing is equal to delta, right? And now we're a little bit stuck here because ideally what we would like to do is solve for tr, but you see there's no real easy way to just get a nice form of tr is equal to something here, right? You'd have to just numerically solve this or graphically solve it or do whatever you like, or heck, just run a simulation and just measure it, because the rise time is actually a very simple thing to measure off of actual data. The one thing to note here is if you look at this expression though here, this is not a function of a. So again, rise time is one of these things that it really doesn't matter how hard you hit the system, the rise time is going to be the same always, okay? All right, so you know what might be helpful now that we've got all of these things written down? Let's make a little table here or a summary of all of the different performance metrics that we derived today here. So we talked about the time to the first peak here, TP. That was given by pi all over square root of 1 minus zeta squared omega n, right? So this was time to first peak, right? Then we had the magnitude at the first peak, or MPT. That was a times 1 minus e to the negative pi zeta all over square root of 1 minus zeta squared here. So here was magnitude at first peak, right? We then had the percent overshoot here was given by 100 e to the minus pi zeta all over square root of 1 minus zeta squared. So here was percent overshoot. And then we had the concept of settling time, or I guess this conservative approximation of settling time, which we said was minus natural log of delta here, all over zeta omega n here. So here was settling time. And finally, we discussed the rise time, which was, I guess, let's just call it numerical. Right? There was no, unfortunately, handy-dandy function here that, or closed form solution for the rise time. Okay, but this is actually really, really helpful, because if you think about this long enough now, what we've actually ended up developing here is this nice set of equations here which predict the performance of the second order system. So as soon as you know zeta or omega n, or I guess maybe the amplitude as well, or how much settling time you want, but as soon as you know these parameters of the system, you can find out and predict what the actual performance of the system is going to be. Or vice versa here, if your manager drops into your lap and says, you know what, I need a system that's going to settle in a specific amount of time, have less than 10% overshoot, and take 5 seconds to get there here, right? You can now see that puts some restrictions on, well, what does the damping ratio and the natural frequency of your actual system have to be? This often, like we said, you might hear this also referred to as time domain analysis. Or, like we talked about earlier, these are also just some performance metrics. So we could talk about, this is the performance of a second order system. This is doing time domain analysis on a second order system. We're evaluating some performance metrics for a second order system. It's all very similar here. It's the same thing. So with this, maybe what we should do here is let's just go through an example of this here. To see how reasonable this is. So the example I'd like to use is the one that I think we kind of started already hashing out in the Mathematica notebook earlier. Let's use an example here. So it's really a pretty darn simple example here, but let's go ahead and just walk through it anyway here. So let's use a step input amplitude of 2.3 units here, and an omega n here of 1.5, and a zeta of 0.2 here, right? So let's just plug all these in, calculate all of our performance metrics, and then look at how they compare to what the actual system did to see if they're actually reasonable. So to do this, let's run over to Mathematica here, because it's much better at evaluating these things than I am at the board.
All right, so why don't we go ahead and run through an example here. All right, so let's go ahead and first compute how about the time to first peak, right? I think we said time to first peak. Whoops, sorry, hold on. I lost my notes. Let me pull that up here so I don't misquote what the actual expression was. Sorry, probably should have had this prepared ahead of time. Oh, okay, here we go. All right, okay, time to first peak here. We said this was a pi all over square root of 1 minus zeta squared times, whoops, come on, where's omega n? Times omega n, right? And then let's go ahead and here, do we already have an omega n given? Yeah, we did. All right, so we had omega n given. Do we have zeta given? Yeah, we had a given. I think we already, these are the values we had defined previously in our example here. So these are the numbers we're using for our particular example here. Okay, so let's go ahead and just make all of these replacements, right? And omega n goes to omega n given. Great. Okay, so here we go. First thing we see, this predicts a time to first peak of 2.14-ish seconds here. So if you come and look at this example, yeah, that looks totally correct. Great. So we nailed the time to the first peak. How about the magnitude at first peak, or MPT? All right, magnitude at first peak was a times 1 plus e to the negative pi zeta. Whoops, pi zeta. This whole thing over, I think it was, what was it, square root of 1 minus zeta squared, right? So here was our, come on, messing up my brackets and whatnot. Here was our expression here, and again, let's go ahead and plug in, or make our substitutions for the numerical values we're using here. Okay, a magnitude of 3.5. So coming back to the picture, yeah, that sure looks exactly right, 3.5. Awesome. Keep on trucking then. How about percent overshoot, right? We said percent overshoot was 100 times e to the, minus pi. Actually, I think it was this thing right here. Oh, come on, mouse. Select that whole thing. There we go. Yeah, that was our expression for percent overshoot here. Oh, whoops, sorry, I forgot to plug in our numerical values here. So we have about a little over 50% overshoot. And again, looking at this picture, yeah, it sure looks like it goes, yeah, about, 50% or a little bit more of overshoot. And then finally, let's get our TS tilde, right? Our conservative estimate of settling time here. So we said that was negative natural log. I always screw this up in mathematics. I think log is natural log here. Of delta all over zeta omega n here. So we're going to go make our substitutions here. And the last thing, we actually also have to pick a delta, right? So let's go say delta, I don't know, how about 0.05%? 5% settling time. So if we hit that, it claims 10 seconds. And I guess if we come and look at this picture, this is going to be a little bit hard to see. But yeah, I guess here 10 seconds is out here. And I guess I'll believe that's 5% settling time here. Okay, so that is pretty much it. I think this is a good spot to wrap up our discussion on time domain analysis. So remember, the important thing that we got out of this now is we've developed a set of performance metrics that are going to allow us to map between engineering requirements, something that a manager or a customer might give you, saying things like, I need a certain settling time or I need a certain percent overshoot. That's going to now tell you as an engineer what are the desired natural frequencies and damping ratios of this system. So on our next discussion here, what I would like to do is take that relationship one step further, in the sense that if you know what your zeta and omega n have to be here, where do you need to put the poles of your system here? Okay, so like I said, that's a little teaser, a little trailer for our next discussion. I hope you'll be able to join us here. If you enjoyed the video, please subscribe to the channel because, like I said, we're going to have more discussion on control theory and classical control coming up here. That being said, I hope to catch you at a future video. Bye.